Hello friends, today we are going to discuss the topic of losses and efficiency of three-phase induction motor, short and continuous rating of the motor. When three-phase AC supply is given to the motor, it converts this electrical power into mechanical power. The mechanical power obtained at the shaft is always less than the input electrical power. This is due to the fact that the motor has many losses in it. These losses basically are stator copper loss, rotor copper loss, stator iron loss, frictional and windage loss. Here we are assuming that the rotor iron loss is negligible due to an assumption that we are taking a squirrel cage three-phase induction motor. Here the stator copper loss and rotor copper loss are the variable losses which depend upon the loading condition, whereas the stator iron loss and frictional and windage loss are basically constant loss, out of which frictional and windage losses are dependent on the speed of three-phase induction motor. Let's try to understand how these losses are calculated of a designed motor. We are assuming that the motor is already been designed and we know the parameters of the stator, hence we can calculate the stator copper loss PCS, which is generally given by 3Is square Rs, where Is is the stator current per phase or input current per phase, Rs is the resistance of the stator. Since we are considering resistance of the stator per phase, we are multiplying by 3, where resistance of the stator is calculated by rho Ts LMTS upon As, where rho is the specific resistivity or specific resistance, Ts is the number of stator turns, and LMTS is the length of main turns of the stator winding. As is the area of the conductor used in the stator winding. So here we can calculate the stator copper loss. On the same line, we can calculate the rotor copper loss PCR. Rotor copper loss, assuming that we are using a squirrel cage induction motor, will consist of copper loss of the rotor bars and copper loss of the end ring. So the total rotor copper loss is given by the sum of copper loss of the rotor bars to the copper and the copper loss of the end ring. We can calculate the copper loss of the rotor bar by using a formula SR IB square RB, where SR is the number of rotor slots, IB is the rotor bar current, and RB is the rotor bar resistance, where the rotor bar resistance can be calculated by using a formula rho LB upon AB, where LB is the length of the rotor bars and AB is the cross-sectional area of the bar. Rho is the resistivity of the copper conductors or copper bars which we generally use. Similarly, we can calculate the copper loss of the end ring by using formula. Since we are using two end rings on both the sides, one each, so we can calculate 2I square Re, where I is the end ring current in ampere, Re is the resistance of the end ring. This resistance of the end ring, this is resistance of end ring, is given by formula rho dE upon AE, where D is the depth of the end ring and A is the area of the end ring. The stator iron loss PIS is generally a constant loss and depends upon the iron material used for the stator. Here we have a stator which consists of the stator slots which are provided to carry the armature conductors or winding conductors. The mean periphery of the stator core is calculated by the outer diameter of the stator core minus the inner diameter of the stator core, from where we can calculate the volume. Volume of the stator core is given by mean periphery into the length into the depth of the slot of the stator. So once we know the value, we can multiply the volume by density of the material used and the weight can be calculated of the stator core. For every material which we use for the stator core, there is a specific loss in watts per kg. If you multiply that watt per kg specific loss by the weight we will get the iron loss of the stator core. So stator core iron loss is thus given by weight multiplied by the specific loss in watts per kg. So we can get the iron loss. The frictional windage losses, which are due to the rotation, basically are constant losses, depends upon the speed of the motor. It also depends upon the type of stator and rotor slots. If the open type of slots are used, then definitely the obstruction provided by the slot opening will be high, and frictional and windage losses will be high because air will be opposed by this opening of the slots. Similarly, we know that there is a thumb rule that for every 100 mm of the stator core length, 10 mm radial ventilating duct is provided. So these radial ventilating ducts will also have an opposition to the flow of air, hence the frictional and windage losses will also increase. So generally there is an assumption which we make that frictional and windage losses are having a range of 1% to 2.5% depending upon the above mentioned parameters. So once we can assume the frictional and windage losses to be a constant ranging between 1% to 2.5%. So the efficiency of the motor is given by the ratio of output power to the input power, whereas the input power is nothing but the sum of output power to the losses. So we can say that input power is equal to output power plus the stator copper loss, rotor copper loss, stator iron loss, and frictional and windage losses. So once we know all these losses, we can calculate the efficiency by the formula. Efficiency is ratio of P out upon P in. Similarly, we know that the motor is required to provide the mechanical output, and this mechanical output will be used for the motor. Depending upon their applications, we can have different types of ratings of the motor. Some motors which are working continuously at the rated output for infinitely period of time without exceeding the permissible temperature rise, basically are having a continuous rating. So here the motor is running at a constant torque for an infinite period of time, so the temperature will rise initially from 0 or ambient temperature to the maximum permissible temperature. So this type of motors are generally known as the continuous rated motors. Few motors are known as short time motors are being operated at its rated output for a certain specified period of time without exceeding the permissible temperature. So these motors are running for some period of time, and after that it is turned off, and there is a large amount of time lapse between the second on period. So it gives a sufficient cooling time for the motor to cool down, and the temperature will come back to the ambient temperature. So this is known as the short time rating of the motor. So motor is used for very short period of time. This period could be 1 hour, 2 hour, and without the rise in the temperature above its permissible limit. And we know that this permissible limit is decided by the class of insulation. So the rating of the motor thus in that case will be known as the short time rating. Thank you. Please like, share and subscribe this.